section, we have our lumen is always the inside of the tube, so inside of the blood vessel would be where our blood is. So the lumen changes sizes depending on what's controlling the blood vessel. This first layer in blue would be our intimate layer with the blood, so it's the intima, and that's just the endothelial cells or epithelial cells found on the inside of the body. And then we have our media, which is our middle layer or our muscle layer. And so this is smooth muscle, and that's going to constrict and change the size of our lumen. When we decrease the lumen size, more blood is in contact with the vessel walls, and that increases our friction. If we open the lumen size up, we have less resistance or less friction. We're going to talk about that a little bit later. And then we have this kind of connective tissue around, should use a different color, on the externa or external layer. So that's called the tunica externa, or also called the adventitia. But the lumen was the key that I wanted to get in, because a lot of times I'll use that term lumen, and we're talking about the inside of the blood vessel, or the size of the inside of the blood vessel. So 60,000 miles of blood vessels. Basically, there are some studies or reports, I don't know if it's a study, but reports that say that for every pound of fat that you gain, you have to have another 10 miles of blood vessels. So let's say you gain 10 pounds of fat, you've got 100 miles of blood vessels that you have to pump blood out. So it's going to take more blood pressure to push blood an extra 100 miles away from the heart and back. And that's why gaining weight makes your blood pressure go up. So simply losing weight can bring your blood pressure down, because you're decreasing the amount of distance that the blood has to be pumped out. Arteries are going to be taking blood away from the heart, and veins are going to be taking blood back. We already know that. The three layers pretty much following this diagram until we get down to the capillaries. When we get down to the capillaries, any blood or nutrients inside the lumen can't get out if we have a thick muscle layer and connective tissue. So we start to lose that as we get down to the smaller and smaller and smaller vessels. If this was a aorta, which would be roughly 3.5 centimeters or so, a red blood cell would be microscopic. So we could line up, we said 5 million per cubic millimeter, and we got a couple centimeters here. You could have billions of red blood cells crossing the lumen in a large artery. When we get down to the capillary size, as I drew before, if we had a capillary, with respect to the capillary, the red blood cell can be almost the same size as the capillary. So in other words, the vessels start off huge with billions of red blood cells crossing or spanning the side to side. As we get down closer to the capillary levels, the lumen is the same size as a red blood cell. In fact, some red blood cells have to squeak through and squeeze and twist their way through a capillary. So these are tiny, tiny blood vessels when we get down to the capillaries. And that's because that's where we're going to be giving off the nutrients and picking up the waste products. So you can see here, this is kind of like if we said, how many red blood cells could you stack across here? Several million or billion maybe even. You come over here, one red blood cell can barely squeak through that vessel. That's how small we're getting down. You can see our three layers. We got our intimas, it looks like epithelial cells if you can see them carefully. They're broad and fat. And then why are they like that? That's because if we look at something like this, see if I can do it. Epithelial cell we saw in lab, they're broad and thin. So if you take these and we fold it up like this, and we made, I can't do it with two hands, if we made a tube like that, or a vessel, if you're inside this tube, to get out, it's very thin. You only have to cross a tiny, thin layer of cell membrane, but we can carry blood all along it. So it gives us this broad tube form that's very thin. So when you're inside a capillary, this is our red blood cell, when you're inside a capillary, to get out is very easy. So the nutrients can cross this plasma membrane because it's very thin, like a sheet of paper. Not quite. Smaller. Okay, so we have the intima, which is the endothelial cells, very thin. We have the media, I think of M for muscle, M for media, and outside is this connective tissue, adventitia or externa. And then as you get away from the arteries, we start coming into these little ones, and little arteries are called arterioles. And these arterioles give rise to a capillary bed, and this would be a capillary bed. This capillary bed can branch. Here it looks like it branches a dozen times. It can branch 100 times or more, and service all the tissue in this area. In other words, we have cells out here that need nutrients. So we have our blood coming into a capillary bed through an arteriole, giving rise to a capillary. This would be our capillaries, so we'd have a red blood cell in there squeezing through, and that red blood cell is going to give off oxygen to the tissue. So everything out here are the tissues, or the tissue space. So we have our skeletal muscles, or our fat cells, or our epithelial cells, or whatever tissue we have. And we're going to be giving oxygen off, picking up CO2, giving nutrients like amino acids and glucose, and picking up waste products like urea and creatine. So this is only branching twice, but it could branch 100 times, and then there's more than just one muscle cell here. We have all the tissue cells there in that area. And if we cut off blood flow here, we can decrease blood flow to these tissues, and those tissues don't get nutrients. So the arterioles are the arteriole, little artery, are the main ones for controlling blood flow. If we want to send blood flow to our legs and our heart because we're going to run from a tiger, we vasodilate, so the arterioles relax, and we send blood flow to all those capillaries. And then if we are running on a tiger, we don't want to send blood flow to our digestive tract. No sense in digesting food if you're going to be food. So we constrict blood flow to the gut, and we can change the blood flow throughout the body. If we're looking at a capillary bed, we can change the flow of blood through a capillary bed via precapillary sphincters. I'm a little ahead of myself. Let's go through some of these and we'll catch up to the precapillary sphincters. So externa is going to be connective tissue. It's going to anchor the vessel in place so that it doesn't get pushed around. It's going to be relatively held in place. You can push some of these veins around. If you look at somebody with big veins in their hand, you can push them and they wiggle, but they don't go very far because the adventitia is anchoring them to the underlying tissue and over the underlying tissue and the skin, and so that they don't get pushed all the way over and tear. They also help keep the vessels from over expanding. If blood volume goes up for some reason, they're not going to stretch out and pop. Did I jump through a couple?
It bounced through.
It bounced through? Okay. So we were talking about, that was the externa, the connective tissue holding it in place. It's going to contain some of the nerves and blood vessels that are going to be delivering controls to the blood vessels. We control these blood vessels with the sympathetic nervous system and the parasympathetic nervous system. And then some of the larger vessels, like the big aorta and the big brachial arteries and stuff, the outside is muscle. There's a thick muscle layer, and then the connective tissue needs blood flow. And so they actually have little tiny blood vessels that come off the vessel and go and feed the tissue. So we'd have blood vessels coming off of this, or I should say, the inner layer here, the endothelial cell gets oxygen and nutrients straight from the blood. They can get what they need. But this big, thick muscle cell needs to have its own blood supply. And so we have blood vessels that feed the blood vessels, and that would be vasorum. I think I have that up there, vasorum. So it's really saying vessels for the blood vessels. They have their own little blood supply because when they get really thick like this stuff is too far away from the nutrients, and it's living tissue. It needs its own blood supply, so we feed it with its own blood vessels called the vasorum. And I put up there, how do the inner layers get nourishment? I just told you, they steal it right from the bloodstream. They can get it. Let's jump back here one. So the intima is in contact with the red blood cells. We said earlier that it has to be really smooth because red blood cells want to slide along the inside of this vessel. If it gets rough, then platelets stick, and we can start getting platelet plugs, which can clot and blood clots. And we keep it smooth in a healthy person, but if with inflammation like smoking and trans fats, it can get rough and things can stick to it. The media is that muscle layer, and that muscle layer is going to control the size of the lumen. So if we want to have it up here, no, I'll have it later in the PowerPoints. Just a small increase in the diameter greatly reduces the friction. And so if you look at this blood vessel as our capillary, and I had our red blood cell in here, that red blood cell, as it moves through, that entire red blood cell is in contact with the vessel walls. So there's a lot of friction. It moves very slow, and it can't make its way through very easily. If we had a red blood cell right here in the middle of the lumen, it's not going to touch the walls, so there's no friction for it. So the bigger the lumen, the less friction there is, the better the flow is going to be. As we tighten that down and we get a smaller and smaller lumen, either by contracting a big one, or as we branch into the smaller ones like the arterioles are smaller just by nature, so more blood comes in contact with the wall, increasing the resistance or the friction. We have elastic arteries, and then we have what are called distributing arteries. The elastic ones are really close to the heart, so they're going to be under pressure, and when we pump blood from the heart into these vessels, they stretch out. It's kind of like an accordion when you, is that right? No. How about a bagpipe? When you blow into a bagpipe, the pressure goes up, and then when you're not blowing into it and you're squeezing down, the flow is going out, and that's what happens. We're pumping blood into the elastic arteries. They stretch out, and then when the valves close, they squeeze down on the blood and force the blood out so that we're pumping blood to the systemic circuit. So what do we have? Same three branches, or layers, excuse me, but now we have those elastic fibers so that it can stretch and recoil, so that's why they're called the elastic arteries. It's going to allow us to take that big stretching of the pressure changes, and when we see that pressure changes, it goes up and down with each time the heart beats. If you look at the elastic arteries do this, they're trying to smooth that fluctuation out, but the pulse, that gives us a pulse. That's what you feel when you're feeling the pulse, is that stretching out and then relaxing of the arteries. So what does it do? It tries to smooth out large blood pressure fluctuations. It doesn't really vasoconstrict, it's just going to be taking that pressure, and it allows a fairly continuous flow, because like that bagpipe analogy, when you pump blood into it and then it squeezes down, the blood is flowing out through the major arteries towards the tissues, and doesn't stop just because the heart isn't pumping. So it's kind of squeezing down and forcing blood out, and we fill it back up with another heartbeat, and then we squeeze it back out into the tissues. It gives us that pulsatile effect at the artery, but it keeps the flow continuously going, so it's not spitting and sputtering. Muscular arteries are also called the distributing arteries. So they're going to distribute blood to most of the tissues. So they're the most abundant. And they're muscular because they have that muscular layer that's going to help constrict blood flow. We did talk about bleeding, where that guy got his arms torn off, and he didn't bleed to death because that artery can constrict all the way down, pinch off blood flow, and keep you from bleeding in the worst case or best case scenario. And that's that muscular layer. It just responds under stress and clamps down and tries to clamp blood flow off. And we usually don't do that in a physiological situation, but we can clamp it down pretty well. You can clamp down blood flow to your fingers, and then you light and cold and freezing, or you can cut down blood flow to your gut. Like if you eat, you're digesting your food, and then you go swimming, and you don't send blood flow to your gut, you get the sciatic. So we can change blood flow throughout the body by that muscular layer, and since they're the most abundant, like how do we take blood flow from away from the gut and to the heart? Those are going to be the bigger arteries, these muscular arteries. When we get down to tissues, the arterioles can also change blood flow, as we'll see later in the lecture. Excuse me.